All right, lecture 2, ventilation. What is ventilation? So the definition of ventilation, and let's write this out together, is when we exchange air. And we're exchanging air between two big structures. Remember, this is bulk flow now, yes? Okay, so this two structures, one is going to be the atmosphere. And two, lung, or I'll just put alveoli. Alveoli, okay? That's ventilation, aka breathing. Breathing, okay? Now, when we have something called a single respiratory cycle, and I'm just doing some definitions for you before we start so we can all be on the same page, speaking the same language. Single, well, we got to spell said language. Respiratory cycle. Okay? Is we're going to have inspiration. It's another term we're going to be using. Inspiration, aka an inhale. And then we have to expiration or exhalation or exhale. Okay, that's a single respiratory cycle. We're going to be doing that in the last lecturette. I just inhaled and then I just exhaled. I should be videoing my face so you can see me doing all this stuff. But can you hear me? All right, just visualize me in your mind's eye. Now, couple things that I alluded to in the previous lecturette is that the lung volumes change during respiration. Okay, and so two things, right? If I have something called hypo, okay, Latin, hypo is below, hypoventilation. This is defined as, boom, boom, respiratory rate is low. I just put an arrow. Low respiratory rate. Now ask yourself, what does that mean? Okay. If the respiratory rate is low, that I'm breathing maybe slowly or shallowly, right? Shallow. Okay. Now, if I have a low respiratory rate, then what's going to happen is CO2 can build up. And if that is the case, right, that I can now have instead hyperventilation. And right, hyper is above normal. So here, this is when my respiration rate exceeds metabolic needs. Yeah, and we get dizzy sometimes, okay? Why is that? Excellent question. I do expect you to answer that question at the end of this lecture. That's a good question. I'll write that down right now. Why does hyperventilation cause you to be dizzy? Write that down and solve that later. We need a little bit more foundations first, which is coming up right now. All right, so now we're going to get into the physics of how ventilation occurs, right? So you need a pressure gradient because remember, I told you folks that air moves from high pressure to low pressure. So we got to create that gradient. And so if you look at this, this is not new for you folks, but remember, if I have a larger gradient, right? Larger gradient means I have a very, very high and a very low. The more gradient I have, we're not going to say concentration gradient, we're going to say pressure gradient. But the more gradient I have, the more bulk flow of air I can get from the atmosphere into my lungs, aka alveoli, okay? Now, This shouldn't surprise you, but the more resistance I have, that will restrict flow. Now, as a reminder, hopefully you didn't forget, right? So if resistance is very, very high, what does that mean? Is my tube large in diameter or small in diameter? Small in diameter, okay? Small diameter tube, right? So if resistance is very, very high, flow is going to be low, okay? Does that make sense? Yes? This is review. Now, let's move on. Now, we got to create that pressure gradient, and we create it via muscles in our thoracic cavity. So there's the diaphragm, there's the intercostals, there's also the scalenes, but I don't want to go there. We're just going to talk diaphragm today, okay? But please be aware that there are other muscles that contribute to breathing, and their job is to change the shape, increase or decrease the size of the thoracic cavity, okay? That's important. So here's your first picture, and what this is showing you is the diaphragm is relaxed, right here, boop, okay? And when it's relaxed, it pushes up against the lung, and it causes it to be smaller. So we're going to introduce this topic called Boyle's Law. Okay, do you folks remember this from chemistry? Oh, this is fun. I love this concept. It is amazing. So volume and pressure are related, and this is how they're related. I'm going to show you. Now, look at just what happened here. When I contract the diaphragm goes straight. Okay, you see the original where it was? Yes. And then it contracts and it flattens. And what's happening here is it increases the thoracic volume. Okay. And so here, if you increase the volume of space or a container, you decrease pressure. Okay. You decrease pressure. Does that make sense to you? Please stop, drop, and roll if it doesn't. If it doesn't make sense to you after you watch this lecturette, just email me, okay? So here, let me just show you folks. Now, look at this drawing. Sorry, I'm pausing and stuttering because one, I'm excited, and two, I don't know where to draw these boxes because the space I have is very small. So I'm going to over exaggerate. So this is my thoracic cavity, this box. Okay, with the diaphragm relaxed up here. Now, when I contract the diaphragm, I'm going to over exaggerate now. It is making the container bigger. So I'm going to make my box bigger. Okay, you folks see what I'm getting at here? When I increase the size of the container, AKA increase volume of the box, yes, I decrease pressure. And this is why. If I have five oxygen molecules in here, and they're all in this small space, right? They're going to be hitting each other and hitting the sides of the wall. Ding, 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 like pool balls or whatever, ping pong balls, whatever you play, okay? Ding, 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 or whatever you watch. Now, they don't have a lot of space. So remember, pressure is measured by amount of gases banging up against the sides of the wall, okay? What happens when I increase the size of the container? Oh, the gases have more room. They're not going to bang and ricochet against each other as much. They're not going to bang up on the walls as much. And therefore, this is relative to each other, compare and contrast, right? This would be a high, I'm going to put high P, that means pressure. And then this would be a low pressure situation because I changed the size of the cavity. You folks good? If not, call me. All right, now, moving on. If I want to breathe in, that's inspiration, right? Is that I need to create a pressure gradient. So if I now increase the size of the thoracic cavity, what can happen now is because I'm comparing these gradients to the atmospheric, ATM. That's another acronym you gotta get. Atmosphere or atmospheric. That's confusing. It's atmosphere or it's also atmospheric. I'll let you write that down because what I did not make sense. All right. Now, ATM is atmosphere. So we got to create a pressure gradient between the atmosphere and the lung, and the diaphragm just did that. So in comparison to the atmosphere, the pressure inside the lung is now lower, and so I can get air coming in. Okay? All right, now, so look at the relationship, right? This is inversely I'm having a hard time talking today. I'm very sorry. Excuse me. I'm gonna swallow my spit. This is inversely related. High volume or larger container, decreased pressure. Smaller container, aka smaller volume, higher pressure. Now, if I want to expire, breathe out, I gotta relax the diaphragm. And you folks see, look at what the drawing is doing. You see how it's showing you the original size of the lungs, and then I relax the diaphragm, and now, of course, I am over exaggerating because I'm going to return my box back to this small size, right? This is very, very small, and so in doing so, I decrease the size of the container, I decrease its volume. The pressure is very, very high compared to the atmosphere or the atmospheric pressure. Therefore, air is going to want to go out. Okay? Before I had to teach physiology, you know how I thought we breathe? Just like the muscles move and we sucked air like a vacuum. That's what I thought. I didn't even know anything about pressure gradients. All right. Now we're all on the same page. You let me know if you have questions. Okay, now we're going to go smaller. So just to recap, what we just did was bulk air flow. Bulk air flow. I'm really stressing this, right? Because getting small molecules inside of the body takes two main parts. Bulk air flow, and then getting the gases inside of our body. And that's where we're going right now, getting the individual gases into the body. So pressure gradients, I want to talk about something called Dalton's law. And, usually when we get into respiration, when we start talking about the gas laws, students are like, oh my God. And it's fun. Love it. Embrace. Okay. Dalton's law. And you don't have to remember the names. Don't remember Dalton. I don't care that you know this name. I care that you know the concept. Okay. Now, it's easy. Okay. Don't stress. Okay. Clear your mind right out. Glutamate. Team glutamate. Dalton's law is when gases, and when we say gases now, these are individual gases. How do you spell gases? 2 S's? Anyway, gases. So for example, for our class, we're going to talk about oxygen and CO2. Individual gases move down there. Here's a new word, a term. Partial pressure, not new, gradient. Okay, so this would be moving down there. Partial pressure gradient means, let me just write it out for you folks, because this is all the language we have to use and utilize, right? So this is from higher to lower partial pressure. Okay, what is this partial pressure you speak of? I can tell you right now, right here. Okay, now in the previous slide, we did bulk airflow of air. That is the pressure of air. But what is air made out of, people? There are so many molecules that make up air. Okay, we have oxygen, carbon dioxide, nitrogen. There's water molecules that is in its gaseous forms. There's all kinds of stuff. So the air that we breathe is not just oxygen or carbon dioxide or both. 50% oxygen, we blow up in here. We would light up on fire. Okay. So when we say the pressure of air, that means the adding together the partial pressure of oxygen, the partial pressure of CO2, the partial pressure of nitrogen and etc. ultimately to get this number. This is something 760 millimeters of mercury. This is how we measure barometric pressure. If you folks watch the news, you folks know all about barometric pressure, right? What happens when it gets cold or it rains? Barometric pressure drops. So barometric pressure is pressure of gases, okay? And we can measure pressure in the body and in the atmosphere. Now, let's talk about what's going on. So here I have two containers. This is the atmosphere, and then this is in the lung, in the alveoli, okay? Now, I just told you folks that the pressure of air, in order to calculate the pressure of air, we have to know all the partial pressures of all the gases that make up the air. And that's it. Okay, don't make it more complicated. That's all it is. We get all the gas, and you're not going to have to calculate anything. I just gave you this magical number, 760. Okay, so we have oxygen, and here you folks notice what's going on. I have different concentrations here. Oh, different partial pressures here. See, sorry, I have carbon dioxide, and then I have nitrogen, and then there's a bunch of other stuff. Okay, water vapor mainly. Now, look at these partial pressures, right, of all the individual gases. Whenever we talk about individual gases, that's when we use the term partial pressure. When we just say pressure of air, okay, air is made out of a lot of different stuff. So that's what I've shown here. Now, which way is oxygen gonna move? Look at it. Go back to your foundations, right? Partial pressure gradients will always move from higher to lower pressure. So in here, oxygen, regardless of what bulk flow is doing, partial pressure of oxygen dictates that it will travel from the atmosphere and go into the alveoli, okay? What about carbon dioxide? Look at the numbers. Yes, it's going to go from the alveoli out into the atmosphere. What about nitrogen? So on and so forth, okay? That's partial pressures. If you have questions, you let me know. Next up, pleural sac. The very important sac that encases the lungs.